Welcome to DAR Tutors for online and home tuition. Today, we're covering a crucial topic in IB Chemistry Higher Level, energy from fuels. This video will explore how chemical energy can be harnessed to power our world and the significant challenges this poses for society. By the end of this session, you should be able to, first, write and balance complete and incomplete combustion equations. Second, compare the efficiency of different fuels using their specific energy and carbon content. Third, explain the greenhouse effect and its molecular basis. And finally, identify the major types of fossil fuels and evaluate their advantages and disadvantages. Let's begin by understanding combustion reactions. Our first objective is to understand and write equations for combustion. Combustion reactions involve a fuel reacting with oxygen, undergoing oxidation. We'll focus on organic compounds like hydrocarbons, but metals and nonmetals can also undergo combustion. The type of combustion that occurs, whether it's complete or incomplete, depends on the supply of oxygen. A plentiful supply leads to complete combustion. In complete combustion, the carbon atoms in the fuel are fully oxidized to carbon dioxide, and the hydrogen atoms form water. Let's use butane, C4H10, as an example. Butane reacts with oxygen to produce carbon dioxide and water. Now, let's balance this equation. A useful tip is to balance the carbon and hydrogen atoms first, then the oxygen. First, we balance the carbon. There are 4 carbons on the left, so we need 4 carbon dioxide molecules on the right. This ensures the carbon atoms are balanced. Next, we balance the hydrogen. There are 10 hydrogens on the left. Since each water molecule has 2 hydrogens, we need 5 water molecules. The hydrogen atoms are now balanced. Finally, we balance the oxygen atoms. On the product side, we have 4 times 2, or 8 oxygens from CO2, plus 5 oxygens from H2O. That's a total of 13 oxygens. To get 13 oxygens on the reactant side, we need 13 over 2, or 6.5 moles of O2. This gives us the correct number of oxygen atoms. Chemists typically write equations with whole number coefficients. To achieve this, we can multiply the entire equation by 2. This gives us our final balanced equation. 2,4H10 plus 13O2 yields 8CO2 plus 10H2O. We have successfully balanced the equation for the complete combustion of butane. Now let's move to incomplete combustion. This occurs when the oxygen supply is limited. Instead of carbon dioxide, we can produce carbon monoxide, CO, or elemental carbon, which is called soot. Let's write one possible equation for the incomplete combustion of butane. Starting with our carbon-balanced complete combustion equation, we need to limit the oxygen. We can do this by converting some of the CO2 to CO or C. Let's say we produce 3 moles of carbon monoxide and 1 mole of carbon. To maintain 4 carbon atoms, this works. The hydrogen still forms water, so we keep 5 H2O. Now, let's balance the oxygen. On the product side, we have 3 oxygens from CO and 5 from H2O for a total of 8. This means we only need 4 molecules of O2. Notice this is much less than the 6.5 needed for complete combustion. This equation shows incomplete combustion due to limited oxygen. Let's work through some more examples to solidify your understanding of balancing these equations. We will start with a problem from the IB Chemistry Data Booklet. The problem states, incomplete combustion of hexane produces unburnt carbon, or soot, and another carbon-containing combustion product. Part A asks, what is this product? The problem mentions incomplete combustion and soot, which is carbon. The other carbon-containing product must be carbon monoxide, CO. It's partially oxidized, not fully. Part B asks, explain why incomplete combustion occurs. This is a direct result of a lack of oxygen. When there isn't enough oxygen to fully oxidize the carbon to CO2, it forms less oxidized products like CO and C. Part C asks for 2 health hazards associated with incomplete combustion. The 2 main health hazards are carbon monoxide poisoning and respiratory problems from particulates. Carbon monoxide is a colorless, odorless gas that is fatal in high concentrations. Soot or particulate matter can irritate the eyes and lungs, leading to conditions like asthma. Now let's tackle the final part of this problem. Part D asks us to outline what we would observe when comparing complete and incomplete combustion. Let's think about a Bunsen burner flame. The blue flame indicates complete combustion. A yellow or orange flame indicates incomplete combustion. So, for incomplete combustion, you would observe a yellow or sooty orange flame. For complete combustion, you'd see a clean blue flame. We've focused on organic compounds, but metals and nonmetals also undergo combustion. Let's explore these reactions. When a metal burns in oxygen, its oxidation state increases, meaning the metal is oxidized. Oxygen's oxidation state decreases, so it is reduced. The type of oxide formed depends on the metal and the conditions. For group 1 metals, the dominant product changes as you move down the group. Lithium forms a normal oxide, Li2, with oxygen in a -2 oxidation state. Sodium forms sodium peroxide, Na2O2, which contains the peroxide ion, O2. In this ion, oxygen has an oxidation state of -1. Potassium, rubidium, and cesium form superoxides like KO2, containing the superoxide ion, O2. Here, oxygen has an oxidation state of -1/2. Group 2 metals, like magnesium, typically form simple oxides. Magnesium combustion is a bright, dramatic reaction that produces magnesium oxide, MgO. Transition metals are even more interesting, forming many different oxides due to their variable oxidation states. Copper, for example, forms 2 main oxides, copper I oxide and copper II oxide. When copper is heated in air, it typically tarnishes to form copper II oxide. The first-row transition metals can exhibit multiple stable oxidation states. The most stable oxides are highlighted in blue in your IB data table. This variability is a key characteristic of transition metals. Now let's turn our attention to the combustion of nonmetals. Most nonmetals burn in oxygen to form oxides, with the nonmetal being oxidized and the oxygen reduced. The combustion of sulfur, for instance, produces sulfur dioxide. The more accurate balanced equation accounts for sulfur's S8 allotrope. We have S8 plus 8O2 yields 8SO2. Sulfur dioxide is a major air pollutant that causes acid rain and respiratory problems. Another crucial combustion reaction is that of carbon. Burning carbon in oxygen yields carbon dioxide. This is the fundamental reaction that powers our world through fossil fuels. In coal-fired power stations, this reaction converts the chemical energy in coal into heat, which generates steam to drive turbines and produce electricity. There is a notable exception to the rule that oxygen is reduced in combustion reactions. This occurs when oxygen reacts with fluorine. Fluorine is the most powerful oxidizing agent, and it forces oxygen to be oxidized, even giving it positive oxidation states, as seen in the unstable oxygen fluorides. This demonstrates an important principle in chemistry. The more electronegative element will always be reduced. We will now compare the efficiency of different fuels. To do this, we'll use 2 key concepts: specific energy and carbon content. Specific energy is the energy released per unit of fuel mass. It tells us how much energy we get for a given amount of fuel. The units are typically megajoules per kilogram, mJ per kilogram. Carbon content is simply the percentage of a fuel's mass that is carbon. This is important because the carbon is what gets oxidized to carbon dioxide, a greenhouse gas. Here's a table showing the specific energy and carbon content of some common fuels. Notice that natural gas has the highest specific energy, while coal has the highest carbon content. This means that burning the same mass of natural gas will release more energy than burning the same mass of coal. Now let's apply this to a worked example from your IB curriculum. The problem asks us to calculate the specific energy of octane, C8H18. We'll need data from the IB chemistry data booklet for this. For octane, the standard enthalpy of combustion, delta Hc, is minus 5470 kilojoules per mole, and its molar mass, m, is 114.26 grams per mole. First, the enthalpy of combustion tells us that burning 1 mole of octane releases 5,470 kilojoules of energy. The molar mass tells us that 1 mole of octane weighs 114.26 grams. Specific energy is energy per mass. So we will take the energy released per mole and divide it by the mass of that mole. Our calculation is 5,470 kilojoules divided by 114.26 grams, which equals 47.9 kilojoules per gram. We can convert this to the more common unit, megajoules per kilogram. Since 1 megajoule is 1,000 kilojoules, and 1 kilogram is 1,000 grams, the value is numerically the same, 7.9 megajoules per kilogram. This is how we calculate the specific energy of a fuel from its combustion data. Now let's look at another worked example to compare the carbon dioxide emissions of different fuels. The problem asks us to calculate the mass of carbon dioxide produced when 100 megajoules of energy are released by burning wood and gasoline separately. Here's the data we're given. For wood, the specific energy is 16 megajoules per kilogram, and its carbon content is 70%. For gasoline, the specific energy is 46 megajoules per kilogram, and its carbon content is 82%. We need to find the mass of CO2 produced to get 100 megajoule of energy. This is a very common type of IB question. Let's start with wood. First, we calculate how much wood we need to burn to get 100 megajoules of energy. We divide the total energy by the specific energy. So we need to burn 6.25 kilograms of wood. Next, we find the mass of carbon in this wood. Since the carbon content is 70%, we multiply the mass of wood by 0.70. This gives us 4.38 kilograms of carbon. This is the mass of carbon that will be oxidized to CO2. Finally, we calculate the mass of CO2 produced. We take the mass of carbon and multiply it by the ratio of the molar mass of CO2 to the molar mass of carbon. This ratio is approximately 44/12. This gives us 16.0 kilograms of carbon dioxide for 100 megajoules of energy from wood. We'll do the same calculation for gasoline. For gasoline, we find we need 2.17 kilograms of fuel to get 100 megajoules of energy. Multiplying by the 82% carbon content gives us 1.78 kilograms of carbon. Then we use the same molar mass ratio to find the mass of CO2, which comes out to 6.5 kilograms. By comparing the results, we see that wood produces much more CO2 per unit of energy than gasoline. It is now 10 minutes into our video. I want to take a moment to invite you to contact DAR Tutors for expert tuition. If you're finding these concepts challenging, or you simply want to achieve the best possible results in your exams, DAR Tutors provides personalized online and home tuition. Our tutors specialize in IB chemistry, as well as A-level and IGCSE subjects, and can provide the tailored support you need. Contact us today to learn how we can help you succeed. Let's continue our lesson by exploring the different types of fossil fuels and their impact. Fossil fuels are carbon compounds formed from the remains of ancient organisms over millions of years. They are non-renewable resources, meaning they form too slowly to be replaced once they are consumed. The three main types are coal, crude oil, and natural gas. Coal is the most plentiful fossil fuel. It forms from buried prehistoric forests under pressure and heat. This process gradually increases its carbon content and specific energy. Crude oil is a viscous mixture of hydrocarbons formed from marine organisms. It's found in underground reservoirs, often with natural gas trapped above it. Crude oil is a raw material for many products, but it must first be refined into fractions like gasoline and kerosene. Natural gas consists mainly of methane, CH4. It forms alongside crude oil. It's often called the cleanest fossil fuel because its combustion is usually complete, producing less carbon monoxide and particulates. To summarize, the specific energy and carbon content are key to comparing these fuels. Natural gas has the highest specific energy and the lowest carbon content, making it a more efficient and cleaner burning fuel, as we saw in our previous example. A major consequence of burning fossil fuels is the increase in carbon dioxide levels in the atmosphere, which leads to the greenhouse effect. The greenhouse effect is a natural process essential for life on Earth. Without it, the planet would be about 30 degrees Celsius colder. Sunlight, which is mostly visible light and ultraviolet radiation, enters our atmosphere and strikes the Earth's surface. The surface absorbs this energy and re-radiates it as infrared radiation, which we feel as heat. Certain gases in the atmosphere, called greenhouse gases, absorb this infrared radiation. One of the most important is carbon dioxide. So, how does carbon dioxide act as a greenhouse gas at the molecular level? The key is its molecular structure. A CO2 molecule has a central carbon atom double bonded to two oxygen atoms. When this molecule absorbs infrared radiation, the energy causes it to vibrate. Its bonds can stretch and bend in different ways, like this. The molecule becomes vibrationally excited. After a short time, the vibrationally excited CO2 molecule releases this energy. It can re-emit the infrared radiation in any direction, or transfer it to another molecule like N2 or O2 through collisions. This process effectively traps heat. A significant portion of the re-emitted radiation is directed back towards the Earth's surface, warming the atmosphere and the planet. The problem is that the concentration of carbon dioxide in the atmosphere is rising at an alarming rate, primarily from the burning of fossil fuels. This increase means more infrared radiation is absorbed and re-emitted, disturbing the Earth's energy balance and leading to an increase in global temperatures, a phenomenon known as global warming. Now that we've covered the core concepts, let's test your knowledge with 5 IB-style practice questions. Take a moment to pause the video after each question and attempt to solve it before I reveal the solution. Question 1 asks for the balanced equation for the complete combustion of ethanol, C2H5OH. Let's work through the solution. First, write the unbalanced reaction. Ethanol plus oxygen gives carbon dioxide and water. Balance the carbon first. We have 2 on the left, so we need 2 CO2 on the right. Next, balance the hydrogen. We have 5 plus 1, which is 6 hydrogens on the left, so we need 3 H2O on the right. Finally, balance the oxygen. On the product side, we have 2 times 2 plus 3 times 1, totaling 7 oxygens. On the left, we have 1 oxygen in ethanol, so we need 6 more from O2, which means 3 O2. The balanced equation is 1 ethanol plus 3 oxygen yields 2 carbon dioxide and 3 water. Question 2 asks for 2 major health risks associated with burning diesel, a hydrocarbon, in an engine. Since combustion in an engine is often incomplete, it produces soot and carbon monoxide. Therefore, the 2 main risks are breathing in particulates, or soot, which can cause respiratory diseases like emphysema and bronchitis, and carbon monoxide poisoning, which is a lethal risk. Question 3 presents a scenario where a substance is burned, and it produces a pale blue flame and no soot. Part A asks for the type of combustion. The blue flame and absence of soot are clear indicators of complete combustion. Part B asks us to deduce the type of substance. A pale blue flame is characteristic of oxygen-containing organic compounds, like alcohols. We know these compounds are already partially oxidized, so they require less external oxygen and are more prone to undergo complete combustion. Pure hydrocarbons tend to have more luminous, sootier flames. Question 4 asks for the molecular mechanism by which water vapor, a greenhouse gas, warms the Earth. The principle is the same as for carbon dioxide. Water vapor molecules absorb infrared radiation emitted by the Earth. This absorbed energy causes the water molecules to vibrate with higher energy. This vibrationally excited water then re-emits the radiation, and a substantial part of it is sent back towards the Earth, trapping heat in the atmosphere. The molecular process is the same for all greenhouse gases. Our final question, question 5, asks us to explain why larger hydrocarbons are more likely to undergo incomplete combustion. Think about the structure of a large hydrocarbon molecule. A large molecule has a high carbon-to-hydrogen ratio and a very high number of carbon-carbon bonds. To break all these bonds and oxidize every carbon atom to CO2 requires a very large amount of oxygen. It's difficult to ensure that every part of such a large molecule comes into contact with a sufficient amount of oxygen to burn completely. This structural complexity and high oxygen demand make large hydrocarbons much more prone to incomplete combustion, which we often see as a smoky, sooty flame. Let's quickly review the key takeaways from this video on energy from fuels. This will help consolidate your learning and prepare you for your IB exams. We began by defining combustion and distinguishing between complete and incomplete combustion. Complete combustion, in a plentiful supply of oxygen, produces only carbon dioxide and water. Incomplete combustion with limited oxygen can produce carbon monoxide and soot. We then saw how this applies to various fuels, including organic compounds, and the different types of oxides formed by metals and nonmetals. To compare fuels, we introduced specific energy, the energy released per unit of mass, and carbon content. Natural gas stands out as having both high specific energy and low carbon content, making it a relatively cleaner fuel. Finally, we explored the greenhouse effect, the warming of the Earth caused by gases like carbon dioxide and water vapor. At a molecular level, these gases absorb and re-emit infrared radiation. Burning fossil fuels releases vast amounts of carbon, increasing the concentration of carbon dioxide and intensifying the greenhouse effect, which leads to climate change. I hope this comprehensive review has strengthened your understanding of this critical topic in IB chemistry. Thank you for watching, and good luck with your studies.